So can you see MATLAB on my screen?
Yes.
Okay. So this is the MATLAB environment. Some of us might be familiar with it, but for the sake of those who aren't really familiar with the environment, I will just give a brief description of what it looks like. So what we are seeing here is the main page that comes up when you open MATLAB. By the left-hand corner, you have the current folder section that shows the files in your current directory where you're operating from. So any file you are loading comes from that directory unless you specify an external path. And any file you save will save in that directory automatically unless you save it to another place. In the middle here, we have the command window where you can enter basic MATLAB commands, such as your standard A equal to 6 assignment, or B is equal to 7, or C is equal to A plus B. So you can just do standard operations similar to your command prompt in Windows or your terminal. Then by the right-hand side here, you have the workspace where the name of the variables pop up. So the A, B, and C that I defined will all come up in the workspace. And up here, you have the main tab where you can open scripts and do other things. So today we'll be looking at fuzzy logic design using MATLAB. And I don't know if we have our MATLAB open. Abdulkadir and Oiza, do you have MATLAB open?
Honestly, no. My laptop that I'm using, I'm in the office. I don't know that class will be online, so I would have came with my personal laptop. I'm in the office, and this official laptop doesn't have MATLAB.
Okay. So that wouldn't be much of a problem. Oiza, what of you? Do you have MATLAB open?
Oisa is she will just
Sorry,
be listening.
Are you talking to me?
Yeah, you need to pay attention. Yes, you've been talking.
Yes, I was. Yes, bro. Okay, I was asking actually if you have your MATLAB open, but if you don't have it open, that's not an issue. Just follow what we are doing in class now, and you have the video available to you later on, and you can practice on your own time. So are you still with me?
Me, I'm hearing you. I don't know what happened to them.
Oh,
I'm hearing you very clearly.
I can also hear him loud and clear, Prof.
Okay. So that's amazing. So let us begin. Now, to use fuzzy logic on MATLAB, one of the easiest and fastest way to do that is just use the fuzzy logic toolbox on MATLAB. So MATLAB comes with a pre-built toolbox in fuzzy logic that you can use to develop your fuzzy logic systems. And this has become quite popular, especially those who work in electronics like Arduino. Some of them rather implement their designs in MATLAB, export the file and convert to Arduino code. So because of its ease of use and user friendliness. So to do that on MATLAB, the first thing you need to do is type fuzzy logic designer. Now, if you would see, the fuzzy logic designer has no spaces. The F is a lowercase f, the L is an uppercase L, and the D is a lowercase d. And the D is an uppercase D. And after you type that, you press enter, then MATLAB would load the fuzzy logic designer. So this is what it looks like. As we can see, this is the interface, the home screen for the fuzzy logic designer. And you can start your designs using this interface. So as we can see up here, we can see a standard fuzzy inference system, or FIS. You have the input, you have the inference, and you have the output. And basically, that is what you'll be working with in your fuzzy design. Because every fuzzy logic system first needs an input from the real world, which is our crisp input. And that real world input.
Can you come back small?
Okay.
Can you come back from the f of x that you say is it has an interface or that things? After the design, you said we should just press enter. This window.
Okay.
This
okay. So let me go back to the MATLAB screen. I can see we have some people who have joined us. Mr. James, you are welcome. Akau,
Thank you, sir.
Welcome too. Umar Lawan, welcome. And Ayib Bami, I hope I pronounced that properly. So just a quick recap for those who are just joining. We are doing the fuzzy logic practical implementation, and we are using MATLAB. So when you open your MATLAB screen, you would come to this interface that you can see in front of me here on the screen. And the MATLAB comes with a fuzzy logic toolbox. That if you have the complete MATLAB package. And the fuzzy logic toolbox helps you design fuzzy systems. It's simple, it's easy to use, and you don't really have to spend a lot of time coding. And that's why a lot of people prefer using this interface because even if they want to deploy to Arduino code, they can. There's a conversion tool online that you can convert the MATLAB fuzzy code to Arduino code. So to access the toolbox, you come to the command window here, and you type fuzzy logic designer. Fuzzy logic designer. So the F is a small letter, the L is a capital letter, and the D is also a capital letter. And there are no spaces in between. You type them as one word. This is called camel casing, where you have the major words represented with capital letters, but there are no spaces in between. So when you type this in the command window, you just click enter or you press enter and it would open. Now, sometimes you might make a mistake and maybe start one of them with a small letter like designer with small letter. If you do that, it won't run, but it would ask you whether you mean fuzzy logic designer, actually how it's supposed to be. But in this case, it's not saying that. It's an unrecognized function or variable because the D has to be uppercase. So fuzzy is a small letter with F. Logic, the L is capital. Then designer, the D is capital. No spaces in between. Then you press enter.
Go on.
And when you do that, you would come, this is the fuzzy logic designer screen that comes up. So this is what you have. This was where we are earlier. And when you open it, what you can see on top here, these three boxes are your basic fuzzy logic system. You have the input, you have the fuzzy inference here, and you have the output. And all this makes up your fuzzy inference system, or you might call it an FIS. If you remember from the theory class, the basic component of a fuzzy system is you have the input from the real world, which is the crisp input that comes into the system. And when that input comes into the system, you have to convert it to a fuzzy input, and so that the inference inside can use the rules to determine what kind of output do you get from that input. And so that conversion of the crisp input to the fuzzy input is called fuzzification. And we mostly use membership functions for that. Then you have the inference, which identifies what kind of output you get from the input. But the inference does not work alone. It works in conjunction with the rules. So you define a certain set of rules. And now those rules will help the inference determine the output from the input you provided. And when the output is provided, the output is a fuzzy output, which cannot be understood or interpreted by the real world. So you have to perform defuzzification to convert that fuzzy output to the crisp output. Are you following me?
Yes.
Okay. Okay. So all this currency I just did now, this English. We'll do it now on the screen so that you get a better representation. So we are going to take a case study. And the case study, the first case study we are taking would be temperature control. So what the scenario is we have a room. The room has a temperature sensor and it has a fan. Now, from that temperature sensor, when I sense the temperature in the room, depending on the temperature, I want the fan to come on or to come off. That's basically what I want to do. So it's just like a temperature, it's like a regulated room, a temperature regulated room, where you have a sensor that can sense the temperature and a fan that can control the temperature. Pretty basic. So in that case, we can design the fuzzy inference like this. The first thing you need to do is clearly define what your inputs and outputs are. So here we have input 1 and here we had output 1. So basically our input will come from the temperature sensor and the output will be the fan.
Yeah, we can't see this thing you are saying, or you do them in future because it's just we are just talking.
No, can you see the screen with the yellow, white, and blue box?
No.
What are you seeing?
Oh, what's command window?
Command window
Oh, you're
only.
seeing the command window.
Yes.
Yeah.
Okay. Maybe what I will do is okay. Let me stop sharing. You know, because the fuzzy window came out in a separate window. So I'll share my entire screen. Now, can you see the yellow, white, and blue box?
Yes.
Okay. So sorry about that earlier. So the yellow, white, and blue box is our fuzzy inference system. So the yellow is the input, the blue is the output, and the white is the inference. So the first thing we need to do is define our input and define our output. Now, based on the scenario I just talked about, our input will now be temperature. So when you click on the box, just single click, the box will be highlighted with a red outline showing that that's the box being highlighted. Then when you come to the lower right side of the screen, you will see information about the variable. You can see current variable, you see the name, the type, and the range. The only thing you would be interested in here is the name of that variable. And I'm changing mine to temperature, which will be our input variable. I know the writing is a bit small, but I think if you can zoom in, you would see what I'm talking about because it's also small on the screen here.
We can see it, no problem.
Okay, thank you. Now, I've defined the input as temperature. Now I define my output. So I click once on the box for output and it will have a red outline showing that that's the box in focus. I come down to the name as well and change it to, let me change it to fan. So now I have defined the temperature and the fan as my input and output. Now, there are many scenarios where you would have multiple inputs and multiple outputs. And in that case, you can still implement your fuzzy system. All you need to do is come to edit, the edit button in the upper left corner, and you add a variable. So you can add either an input, and then you will see the screen will change with 2 inputs. You can add another input if you want. It will change with 3 inputs. And you can also do the same with output under add variable. So depending on how many inputs or outputs you want, you can always add multiple inputs and multiple outputs. But in this case, we are only dealing with 1 input and 1 output. So I would highlight and go to remove selected variable, highlight the one I don't want, go to edit and remove selected variable, highlight the output I don't want, go to edit and remove selected variable. So we are now back to our single input and single output. Now, what's the next thing you do after you define your input and your output? You now have to specify. So if you look at the lower left corner, you can see the AND method, which is minimization, the OR method, which is maximization, the implication, and the aggregation. So all these are pretty standard for a fuzzy logic system, unless you have specific, let me say, preferences that you want to change. I would recommend that you leave these as they are. The only thing that you could play around with is the defussification method, which is the last thing there. And when you click on the drop down, you'll see different defussification methods. However, the centroid defussification is one of the most commonly used because it's more like a weighted aggregate. So a lot of people prefer that because each of the components are represented in that case. So, so now we have our input, we have our output, we have our defussification method. Now we have to define the membership functions. Now, what do these membership functions do? They transform the crisp input to a degree of membership from 0 to 1 from our notes. So in order to do that for the membership function, you double click either the input or the output. So let me double click the input and it will bring up a membership function editor. Can you see the membership function editor?
Yes.
Okay, great. So what you have here is by the left, you see your FIS variables, your fuzzy inference system, the variables we've just defined, temperature and fan. And on the right, you see the membership function plot. So what we are to do here is define our membership function for both the input and the output so that it can convert it from the crisp input to the fuzzified input. So starting with the temperature now, if you remember from the theory class, there are several membership functions. You have triangular, you have Gaussian, you have trapezoidal.
Rectangle.
The rectangular is the trapezoidal.
Okay.
Yes, that's the one that's more like a rectangle. Now, in terms of designing, you don't necessarily have a membership function that is better than another. So there is no written rule in literature that this membership function outperforms this. Of course, when you are designing, you could have varied performance depending on the membership function, but there is no rule that this outperforms another. So this is where mostly your design skills come into play in selecting the membership, in developing the membership functions, and in developing the rules. Because when you develop this, it might not give you the performance you really desire. So you have to come back here and tweak them a little bit. So, but one of the common ones used is the triangular membership function. Another common one is the trapezoidal, because the vertices of the triangle and the vertices of the trapezium are the parameters that people play around with. So what I do here is, for the temperature, let's work with a trapezoidal membership function. And for the fan, let's work with a triangular membership function. You can mix up the membership functions. But I would suggest that for a particular variable, all the membership functions should be the same, then you can change it in the next variable. So for temperature, let's define our membership functions. What I usually recommend people to do is you go to edit and remove all MFs, remove all membership functions. So when you do that, you start with a clean slate that you don't need to worry about. So like I said, I want us to work with the trapezoidal membership functions. So when considering temperature in the room, the temperature can be hot, it can be cold, it can be warm. You can define the membership functions depending on your own understanding of the problem. And that's one thing about fuzzy logic. If you don't understand the problem you are working with, it's difficult for you to develop an accurate solution for that problem. So in this case, since we are trying to measure the temperature and control it, what kind of temperature are we measuring? The fuzzy logic, if you remember from the introduction of the fuzzy logic, is a technique that deals with vagueness and uncertainty. So in our day-to-day life, we talk about hot, cold, warm. But if I ask everyone in the class that what temperature is water hot, what temperature is water warm, and what temperature is water cold, I'm sure I'm going to get different answers from everybody. We all know that 0 degrees is freezing and 100 degrees is boiling water. But what about warm water? To some people, 50 degrees is even hot. And to some people who, there are people who can drink tea all day with boiling water. Some of them will feel 50 degrees is not even hot, it's just warm. So that variation in definition by different people is why fuzzy logic is quite interesting. The same thing if I talk about a height of a person. You can say somebody is tall, short, or average, but at what height does tall start from? At what height does average start from? So things like that. That's why we use fuzzy logic. So in this case, we want to measure whether the temperature is hot or cold. So let me give a range of temperature. Let me say the temperature starting from 0 to, let's say, well, atmospheric temperature. Let me just stop at 70 degrees. Although sometimes you can have negative temperature. So let me start from -10 to 70. What I'm doing on the lower left-hand corner, you would see the information about the variable, the name of the variable, the type. I'm modifying the range, just the range, not the display range. So my range takes two values, the lower boundary and the upper boundary, from -10 to 70. So now I can add my membership functions. Let's work with 3 membership functions now for simplicity. Let's have cold, warm, and hot. If the temperature can be cold, warm, or hot. So you come to edit, you go to add membership functions, then another screen pops up. Then you select the membership function type. This try-mf is triangular membership function. Trap-mf is the trapezoidal membership function. So you can see Gaussian bell, G-bell, you can see Gaussian, you can see sigmoid, you can see many types. So let's work with the trap membership function, which is the trapezoidal membership function. And here you can also select the number. So let's stick with 3 and you click OK. And now you can see that it has added membership functions automatically for you. And if you see MF1, MF2, and MF3. And on the x-axis, you will see that it's from -10, which is the range we defined, to 70, the lower and upper bounds. But if you look at the y-axis, you will see that it's always from 0 to 1. Yes, the definition of membership function, it transforms the crisp input to a fuzzy input using a degree of membership from 0 to 1. And that's why it's only 0 to 1 on the y-axis. It cannot go higher. So now let us define the membership functions. We have 3. We said the first one, the MF1 is going to be cold, MF2 is going to be warm, and MF3 is going to be hot. So if you click on any of the membership functions, it will change to red, meaning that that's the one selected. And you can come down to the lower right corner and change the name. So the MF1, I'll change it to cold. MF2, I'll change it to warm. Yes, and MF3, I will change it to hot. Okay, good. So now I'm going to ask some questions. So let me bring up the names. Let me start with Abdul Qadir. What do you think the temperature for cold should be? Normally, in the environment, what range of temperature would you consider to be cold?
Okay, thank you. It's a function of the location. In tropical region, we consider less than 10 as cold, but in tropical, in Europe and other places, minus 10, minus 5, anything below 0 is what they consider as cold.
Okay, so will it be fair to say, based on our range now of minus 10 to 10, sorry, our lower range of minus 10, considering we're in the tropical regions, we can say, okay, minus 10 to 10 should be considered cold.
Considered cold, that is fine.
Okay, so you have two ways of doing that. Number one, you can either click on the membership function and drag it so that the lower part can be on minus 10. The other part, you can bring it to 10, and you can adjust the top the way you want. So it's quite interactive. So I still need to, sorry. Okay, so I can do something like this, saying that my first membership function for cold lies between minus 10 and 10. I can drag it manually, but sometimes it's quite difficult to get the correct shape if you drag it manually. So you can come to the lower right corner where you see params standing for parameters, and you can input 4 values. These 4 values stand for the vertices, these vertex boxes on the membership function. So we can say our lower boundary is minus 10. Then let's say the middle, the first middle part, let's leave it at minus 5. Then the second middle part, we can say plus 5. And the last part, we can say 10. And when you click enter, it adjusts itself automatically. So you can see that it's 10 minus 5, 5, 10. So that is for cold. For cold. So let's do that of warm. Is that with us?
Yes, yes.
Okay, so what range of temperature would you consider to be warm? And mind you, the temperatures can intersect. So just because Abdulkadir stopped at 10, it doesn't mean we have to continue from 10. If you feel 5 degrees is warm, you can say 5 degrees is warm. So
Okay, I think maybe 20.
Okay, 20.
Yes.
Okay, 20 to what? Or 10 to 20?
Yes, 10 to 20.
Okay. So in that case, we can come to parameters. Our lower boundary is 10. 10 to 20. No, 15 is too high. Let's say 12.5. Then we can do 17.5. Remember, there are 2 middles. It's not one middle.
Okay, okay.
Yes.
So the next one should be 20.
Yes. So, okay. So now this is what we consider as warm. Okay. Aibami.
Okay, Engineer Bala, these numbers, are they not supposed to be uniform, like the intervals between them? Like this one, the last one we have minus 5, minus 10, 5, 5, minus 10, minus 5, 5. It's like you are just having incremental value of constant incremental value. But in this case, the incremental value is not constant.
So for warm, you can see that it's smaller than cold.
Yeah.
Yeah, it doesn't. You don't necessarily have. It doesn't have to be the same. That's beauty about it. You can use any design pattern you want, depending on the kind of results you are expecting. Sometimes for, should I say, uniformity or consistency, you can use the same ranges, but at the end of the day, the design is up to you. There is no rule of thumb. Some people, when I was telling her that it could intersect, there are some people that would specify that, okay, between one membership function and another, if it's intersecting with the other, like what I'm doing now, the intersection should happen at 0.5. Like what I have here now, the intersection should happen at 0.5. That's what some people would specify, but there is no hard rule that it has to be like that.
Any advantage for that?
No, not really. You know, the whole idea of the fuzzy logic design is people have varying opinions of cold and warm. Now, in this case, your cold boundary is 10, and OISA decided to start her warm boundary from 10. But there are people who might consider 15 degrees still as cold, and those same people might feel, okay, maybe 12 other people might feel, okay, 12 degrees is also warm. So in that case, you're going to have an intersection either way. So at the end of the day, it depends on your design and your understanding of the subject matter. And that's one thing that some people might tell you they don't like about fuzzy logic, because there are no standard rules to guide you. It all depends on the designer. And the accuracy of the design depends on the designer's experience. Like the example you gave us, that tropical regions and temperate regions have different perceptions of their temperature, which means it's either you design something that is generic for both, or you have separate designs for tropical and temperate regions. I don't know if that's clear.
Yes, clear. Thank you.
Okay. So let's continue. Ibami, I'm coming.
Okay, sir.
I want to put back the values we selected. Okay, then warm, we started from 10. And 12.5, 17, 75, and 20. Then, and mind you, even the way I'm designing the trapezium, that I want the distance between one vertex to another to be uniform. If you like, you can decide not to do it like that. If you like, you can have one part more slanting than the other, and the other part straight. So it's completely up to the designer. So, Aibami, what do you think our range should be for warm?
For warm,
For hot. Yes.
Yeah, I think I would start my hot from around mid 20s. Let's say 23 to 33, mid 20s to mid 30s.
Okay, so anything higher than the 20s should be considered warm, because it's not really advisable for you to leave a portion blank. If we start from 23,
okay.
It means from 20 to 23 is not represented.
Yes.
Okay, so let's do 20 to 70.
Okay.
20, the midpoint. Okay, let's do 20, 30, 60, 70. Okay, so you can see what I was trying to explain earlier. For our hot, the distance between the middle vertices, the interval is not really uniform. You can see that the hot membership function is more slanting than the others. So it's all based on the design. So now we have the cold, warm, hot. Let's go to the output. You go to the lower left corner, click on fan, and it comes up with the membership function plots. So like we did earlier, we remove all membership functions because we want to start afresh. And for our fan, let's have off, medium, and high. So it's either the fan is off, or the fan is rolling at the medium speed, or it's rolling high. You know, our standard fans usually have numbers 1 to 5. So in that case, if you feel you want each number represented, you want a membership function for 1, for 2, for 3, for 4, up to 5, you can do that. You can do as many as you want. But for the sake of this class, I'm sticking with 3. So I'll go to edit and add membership functions. In this case, I'm not going with trapezoidal, I'm going with triangular, and I'm sticking with 3. And you can see the way triangular is represented. You don't have a trapezoid, a trapezium, you have a triangle. And that means triangle would have 3 vertices, which means you only have 3 parameters to play along with. So is Akau with us? Akau, are you with us? Okay. What of James? James, can you hear me? Hello, James.
Yes, sir. I'm hearing you, sir.
Okay. So for our fun, we want to take off, medium, and high. So I specify the range from 0 to 5, which is our standard fan speed that we have in our fans here. The first membership function would be off. I will rename it to off. So what do you think our range should be for off?
In terms of what? I thought that off should be 0, medium should be 3, and the other one will be 5.
Okay, so that's the way you want to define it. The off should be 0, medium should be 3, and high should be 5.
5, yes.
Yes, okay. You can do it that way. In that case, let me say for off now, I can just define a tiny range around 0. Let me say 0, 0.1, and 0.2. And I'll have something like this to signify off.
Okay.
So what about for medium? Is Umar with us?
Yes, sir.
Okay, do you also think 3 should be medium?
Yeah, it's okay. Three can be medium. Let's say maybe from 2.5 to 3.5.
3.5, okay. So I'll put 2.5, 3.5. So if you see here, we are dealing with 3 parameters because they are triangles. But you can also deal with 4 for trapezium. So for Gaussian functions, you know, you are dealing with the curve. So you can play around with different membership functions at your free time. Then the last one would be high. Is Akao back? Okay.
I've been here like
Oh,
yes, I didn't go anywhere.
okay. So do you think 5 should also be a high? What range should we put for high? Okay, let's continue. For high, based on what we've been doing.
Take 4.5.
Okay, 4.5.
4.5 and 5.
4.5 and 5. Okay. Okay. Now, as you can see, our membership functions, there is a large gap that is not represented. For the output, this isn't always a problem because it means whatever output you are getting is between these ranges. But in our fans, I think if you put it at 1, okay, 1 might be considered low, but 2 and 3 also can be considered medium, if I'm not mistaken. Then 4 and 5 also can be considered high. So why not we expand the membership functions so that they can at least, so that we won't have any area that is not represented.
That is not covered.
Yes. So for zero, let me say from 0 to 1, anything lower than 1 should be considered off.
As 0. Okay,
yes.
off.
Yes. I'm not saying this design is wrong. No. What I'm saying is I don't want to leave any space unrepresented. So that's why I want to expand the designs. But you can also work with designs like this. I've done designs like this in projects that we've worked on. So, but for this course, I want to expand. So let me do 0.5 and 1 for the 0 so that I can expand it. Then from medium, I can do, let's say 1 to 4. So I can do 1. No, sorry. Yes, 4, 5 should be high. Medium can be 1 to 3. Okay, 1 to 3. So let me do 1, 2, 3. So that it can be wider. And for the high, let me say anything higher than 3 is high. So let me say 3, 4, 5. Okay. So now we have our membership functions. The next thing we need to do is define our fuzzy rules. So in that case, you go to edit and you select rules. Now, what you do here is just specify the rules that would determine the operation of the system. Now, in the rules, if you remember from the note, it has two parts. It's basically if/then. So the if part is usually called the antecedent, and the then part is called the consequence. So the if is the condition you are given. If whatever input meets this condition, then my output should be this. So let's start here. You can see the white box above here is where the rules will be listed as you are inputting them. You have the if part over here, and usually the if part takes all the inputs, but since we have only one input, we have temperature. If temperature is whatever that is here, then you have on the right side, you have the then fan is this. So basically you're saying if temperature is this, then fan is that. Just like your if else statement. So over here you will see not. Not is used for toggling or inversion. So you could say if temperature is not this, then fan is that. Maybe if you don't want to use the standard if, you want to add an inversion that, okay, if the temperature is not hot, then the fan should come on or something like that. Then you have a connection. Usually the connection comes when you have multiple inputs or outputs. So let's say we were considering both temperature and humidity, for instance. You could say if temperature is high and humidity is high, then the fan is high, for instance. Or if temperature is high or humidity is high, then the fan should be high. So that's why you have the connection. But in this case, since we only have one input, it doesn't count here. So let's start. If the temperature is cold, we want our fan to be off. If it's cold, you don't want the fan to keep blowing you on top now. So you select cold under if, then you select off under fan. And then in the middle here, you will see add rule, then you add. And the first rule will come up. Now, if the temperature is warm, if it's not too hot, maybe those in Abuja, maybe the temperature over there is warm. So in that case, you would want your fan to just be medium, so that at least you wouldn't feel the warmness if you still want to feel chilled and everything. So you select warm and you select medium and you add the rule. And now the second rule is there. But for people like me, Mina, if the temperature is hot, I want my fan to be very high so that I will not sweat. So I will select hot and I'll select high and I would add the rule. And now we have basically our rules. Now, like I said, fuzzy logic is a matter of design. There are people who like heat. So if you feel, even with the hot temperature, you don't want your fan to come on, you can say if temperature is hot, then fan should be off. It's completely up to you. Or if you don't mind the cold, if you are used to staying in the cold, you can say if the temperature is cold, your fan should still remain high. That's completely up to you. There is, like I said, there is no, should I say, hard rule on how you make the design. But in this case, if you are designing a temperature controlled room where you want the temperature regulated, these are the basic rules that you work with. And you can also delete a rule. You can change a rule if you make a mistake. So it's quite, should I say, interactive and modifiable. Now, after we've defined the rules, basically we are done defining we are basically done in defining the fuzzy inference system. What you can do is you can view the rules you've defined, and it comes up in the rule viewer. So you can see how all the rules are represented. Here, if the temperature is cold, the fan is off. If you remember the way the membership functions were designed, here, if the temperature is medium, the fan is medium too. That's if the temperature is warm. And here, if the temperature is hot, the fan is hot. So you can put this. And you can also play around here, put some inputs.
Sorry, why is it that the output function has 4 representation while the input has only 3?
Okay, thank you for that question. So the output has 4 because this last one is the aggregation of these inputs.
Of the 3?
Yes, it's an aggregation of the 3.
Okay.
Yes. So
is that always constant like this, or this is unique for this?
No. Whenever you define a fuzzy inference system, you would always have one more at the output, because the output needs to be aggregated. Then that aggregation would be defuzzified to the final output.
Okay.
This is why it needs to be aggregated. Let me give an instance. If we go back to let's go back to our membership function. If you can see the temperature here, the cold starts from here, right? It ends at 10.
Yeah.
And the warm begins at 10.
Yes.
Good. So if you put in a temperature that is 10, will it be considered cold or will it be considered as warm?
Both.
Exactly. So when you go back to viewing the rules, if you put in a temperature that is 10, it will come to cold and take the corresponding value for 10 under cold and put it here. It will come to warm and take the corresponding value under warm and put it here. It will come to hot. Since it doesn't have any corresponding value under hot, this one would be 0. Then it will aggregate these values here before it gives you an output. And that is why the output always has the aggregation. The same thing if there is an overlap where you have a value that falls between 2 membership functions or 3, you always need to take the output from each of the membership functions and aggregate them before you deposify. So that is why you would always have one extra down in the output. So for instance, now if we put here an input and we put 10 and we click enter, this is the value it's giving us on that 10. But I don't know. Okay, yeah. So if you look at up here, you see temperature is equal to 10. The fan speed is given as 2.5. You can say if the input is, let's say if the temperature is 50, which is quite high, you click enter, the fan speed is 4. You can see that the fan speed is high. If the temperature is very low, let's give it a 0 value, then the fan is 0.5, which is still under our off value. So basically, you've designed the fuzzy logic control, temperature control system. Then you can also view the surface plot. Basically, what the surface plot does, it shows you a representation of the input against the output. So if you have multiple inputs and multiple outputs, you will always get a 3D plot. But here, because we are dealing with 2 inputs and 2 outputs, we have only a 2D plot. So when you finish, when you define the membership functions and you define the rules, you can go back to the home screen. You can come to File, and you can export the fuzzy inference system that you've designed. Now you have 2 options. You can either export to File or export to Workspace. So let me do both so that you can see what they mean. If I export to Workspace, it will come up with export to Workspace, and it will ask you the Workspace variable. What this does is it's going to export your fuzzy inference system as a variable on MATLAB itself, the MATLAB workspace. So let me change this to my workspace FIS, for instance, and I click OK. When you come to MATLAB, under the workspace value, you will see my workspace FIS here. And the value is a 1x1 fuzzy inference system, which means anytime you want to use it, you can just simply call the FIS from here, my workspace FIS. And how do you use it? on how do you use it on the MATLAB workspace or the inference? You know, when we finished the designing, I went to view rules, and here I can just put any input I want and I can monitor the output. But sometimes if you are writing a code or a script, you want the fuzzy logic to be part of that code. So in that case, you can use this in your code. Maybe you want to save a variable called fan speed, and you can say it's equal to, okay, before then you need to specify what your FIS is. So maybe you can say FIS is equal to my
Workspace.
FIS. And you now have a variable FIS. But if it's already in the workspace, you don't really even need to define it. You can use it directly. And then, you know, in MATLAB, because I didn't put a semicolon here, all the processing it did, it will display on the screen. So usually we use the semicolon to suppress the output. So it's showing you the name of the FIS, the AND method, the aggregation method, the falsification method, the inputs. You have one input, which is 1 by 1, one output, and you have 3 rules. And then you can now use it. You can say fan speed is equal to, you use the value of eval piece, which means evaluate FIS. That's the function for evaluating a fuzzy inference system in MATLAB, eval piece. But depending on the version you are using, the arrangement would be different. What do I mean? Now, eval piece takes 2 variables. It takes the FIS and it takes the input. But if you are lower than 2018, I think it takes the input before the FIS. Basically, before 2018 down, it's either FIS before input, and 2018 up is input before FIS. So let's try here. We can just say my workspace FIS, and we give in an input value. Let's give our 10. You can put it in square brackets if you want, and let's say 10. So eval phase, the FIS value, then the input value. You know, we are taking only one input, so you can put 10. And you click OK. And now it has evaluated, and it's giving you a fan speed of 2.5. So, but if this doesn't work for you, if this method, sorry, if what I did here doesn't work for you, maybe you have a lower MATLAB version, maybe I think it's from 2018, then you need to put the 10 before my workspace eval. So it will be 10, comma, my workspace FIS, and that's what you do. So if you click this, oh, in both cases it worked for me, but it's giving me a syntax error where you put the eval before the fix. It will be removed in a future release because the order is basically just the order that has changed. So work with FIS before input. If that doesn't work, then you can put the input before FIS. But the function is eval fix. So are you with me on this? Can we continue?
Yes, please continue.
Okay. Now that is for if we're exporting to the workspace. Remember what we did was export to workspace. So what I want to do now is I want to export to 5, not to workspace. In that case, what if we export to workspace, whenever you close MATLAB or you clear the workspace, your FIS has gone there completely. So what you normally need to do, or what I recommend that people do, is you export to 5. And this will save it as a file on your computer in that directory that you are. And I'll also save it, instead of my workspace FIS now, I'll save it as my file FIS, and I'll save. And you will not see it on your workspace. However, you will see it on your file, your FIS file here. So which means whether you close MATLAB or you clear the workspace, this FIS file will always be there. So I would recommend that in most cases when you want to export, always export to file, so that if MATLAB closes accidentally or your system goes off, your FIS is still safe. But in this case now, you cannot use it the way we used it earlier. You have to load the FIS. You have to load the FIS first, and when you load it, that's when you can use it. Yes. So what you do basically first is to load it. Let me call it my FIS, and I'll say it's equal to. Now the other one, you know, we did evaluate FIS, eval fees. This one we are doing read fees, read FIS, and then we put the name of the FIS inside as the parameter. So I'll say my file FIS.fis.
What's the difference between this, my file, and my workspace that you area save it with?
Yes, I was just trying to show the difference between what we saved in the workspace and what we saved in the file. That's why I used different names. Yeah, so when I was exporting to workspace, I saved it as my workspace FIS. But now that I'm saving it to file, I named it my file FIS. It's just the name so that we can know that I'm working with different types. So when you do this and you click enter, still it will give you the same thing it gave us earlier, but now you have my FIS as a variable in the workspace. And then you can now do the fan speed is equal to eval this, my FIS, comma, 10. And when you click enter, we still get the same 2.5 that we got earlier. Now, some people might show you that you might not necessarily have to put these square brackets. You can just put the 10 like that, and let's see if that would work. It still gives you the same value, but I would recommend that always make it a habit to use the square brackets, because if time permits, and we'll do another example quickly, that we have two inputs. You have to specify them in a square bracket as a matrix. So that you would not forget, that's why I would recommend that always use the square brackets when putting the input. Now, before we go to the next example, I want to show you one more thing quickly, how to use the FIS. So I showed you how to use your developed FIS in the Fuzzy Logic Designer, where you go to view rules, and then you can put the inputs here and get an output on top. Then I also showed you how to export to workspace, and I also showed you how to export to file. Now, for those of us familiar with MATLAB, we know that there is a component of MATLAB called Simulink. And mostly it's used for simulations and drawing block diagrams and developing models. So sometimes you might have the Fuzzy Inference System as a file, but you don't want to use it here on MATLAB. You want to use it in Simulink. So I'll just show you how to do that. If you want to load Simulink, you can just type Simulink, or you can come up here and click Simulink. For my system, it will take time to load Simulink, but it's initializing. So in that case, Simulink has blocks. Just a recap of how it works. You have different blocks that you can drag and drop to create a model, basically in MATLAB. Sometimes, if you want to develop a model, if you don't want to develop it mathematically with the equations, writing the equations as a script on MATLAB, you can drag and drop different components on Simulink so that it gives you a better representation. So in that kind of situation, sometimes you might want to incorporate the fuzzy logic into the Simulink itself. And in that kind of situation, that's what I'm going to show you what to do. So let me, this is the Simulink start page. Let me click on create model. For some earlier versions, it might not show this start page, but it will just take you to the blank model screen. directly. So we'll wait for it to load. So this is quite useful, especially if you want to do projects and maybe there is a technique being used that is maybe conventional, and you want to incorporate some sort of artificial intelligence in it, and you decided, okay, I'm going to work with fuzzy logic, but you've built a model in Simulink. You can also use the FIS you developed in Simulink as well, and you get good results with that. So it's taking time to load. So this is the Simulink environment. What you do here basically is you drag and drop various components to build your model, any model you're doing here. So I know there will be some of us in power, some in control, some in computer vision. If you decide that you want to build your models in Simulink, then you can incorporate fuzzy logic. So you go to the library browser, which is a button up here. The library browser will basically load the components for you so that you can drag and drop the components. So you can see different components here. So if you come by the left-hand side here, you will see Fuzzy Logic Toolbox. And when you click on Fuzzy Logic Toolbox, you see the different components of Fuzzy Logic. You see the membership functions, Fuzzy Logic Controller with rule viewer. Basically, if you've defined the Fuzzy Logic and the Fuzzy Logic designer, all you need is the Fuzzy Logic Controller. So you can right-click and you add block to model. Then, so now it has added the Fuzzy Logic Controller block to our blank Simulink model. I would need two more components. One for me to enter to specify the input, and another one for me to visualize the output. So let me come to commonly used blocks. I can see constant here for, what are they calling it? For entering a value. You can also find constant under source. You know, the source is mostly represented as the input. So you can see constant where you right click and you add block to model. You don't necessarily have to use the constant. Depending on where you are getting your input from the model, you can simply tap that into the fuzzy logic. But because we're entering the numbers manually here, I'll use constant. Then if you go to sync, you will see where you can visualize the output. So let me go with display and add that to my model. So now I can minimize the model browser, and you can see all the components have been added on my fuzzy logic. So let me expand them. This is the constant here. This is the fuzzy logic controller here, and this is the display here. Although the display is quite tiny, so I can just connect these blocks. And now I have a simple fuzzy logic model. So the first thing I need to do, the fuzzy logic controller, when you double click, it will bring up the properties of that fuzzy logic controller. And the only thing you need is to specify the FIS name that we can see here. Specify the FIS name. So the FIS name that we have there, I think, is my file FIS. Don't forget to put it in. Why is it showing yellow?
In case sensitive, as you have put it.
Yes, it's case sensitive. How you saved it in your file, that's exactly how you are going to call it here. Then my file FIS, I think you need to put .fis.
Yes, that's the extension.
Yes, so when you click OK. Yep, so your FIS should be loaded. So let's put in a value for constant here. You double click and you just put a constant value. Let's still stick with our 10. Why I keep on using 10 is I want to show you that irrespective of the method you use, as long as you design the FIS, you should be expecting the same results. So it's not that it will change depending on the method. So when you do this, you click on run up here, and it will run the model. Sometimes it will ask you to save the model first. There's a progress bar below that shows it's compiling. Usually for the first time it's compiling, it takes a lot of time, but subsequently it gets a bit faster. So what we have here, you can see that it's a simple fuzzy logic block that you can put in the input and see the output. But some of us would develop very complex models in MATLAB, and there will be some decisions you might need to take. And this is a fun way of bringing novelty into your work. Maybe there are some certain decisions that you need to take that maybe have been taken either by trial, by error, or using a standard equation. Maybe your own novelty could be, okay, I want to, instead of using that method, I want to use fuzzy logic to take that decision. So you can do that in this case. Although another thing is because of its ease of implementation and simplicity, a lot of people have used it in many areas. So you have to find a really unique way of incorporating the fuzzy logic into your design. Okay, it's still running, but it has finished running. I know it's quite tiny, but if you can see in the display block, you should still see our 2.5. Maybe if you zoom in on your device under display, you should still see the 2.5.
I'm zooming in.
It's still small, Ko?
It's okay. It's okay. I can see it.
Okay. So you can still change the constant to 25. You can run it again. And you can see this one is a bit faster now, and it has changed to 4. So that's how, yes, you can do that in fuzzy logic. So I would want us to take one more example so that I can just show us how to deal with multiple inputs and one output, just to give us an understanding. That one would be a bit faster. So should we take a short break, maybe 5 or 10 minutes before we start that one? Or can we fire on?
I think you can fire on.
Okay.
I don't know if anyone wants to.
Okay. We should just continue, right?
Yes, I think you can continue.
Okay. Okay. So now this one will be a bit faster since we're familiar with the process. I just want to show us how to develop a fuzzy inference system with 2 inputs. You can have as many inputs and outputs as you want, but now we are going to just use 2 inputs and 1 output so that you can see how we can connect with and or, and also you can see the difference when we want to, what are they calling it, when we want to develop when we want to evaluate the FIS. So now let's go through the processes again. When you open MATLAB, one of the first things you do when you want to start the fuzzy logic is type fuzzy logic designer. Yes. Remember, F is small letter, L capital, D capital, no spaces in between. Yeah. When you click enter, this is the screen that should come up. Now, the next thing we do is we define our inputs and we define our output. Now, in this case, we want 2 inputs. So we go to edit, we go to add variable, and we add 1 more input. And the screen will now change, showing our 2 inputs and 1 output. Now, the scenario I want us to take here is a popular example in MATLAB under fuzzy logic. One of the first examples you'll come across when you're developing a technique in fuzzy logic. It's called table for 2. What the scenario basically is if you go to a restaurant, I know we don't really tip our waiters or waitresses in Nigeria, but I think it's a common practice outside Nigeria. So if you go to a restaurant and after you've finished eating, you decide to give a tip. But what are those things that would make you, what are those parameters that would influence the kind of tip you would give? It's number 1, the service of the restaurant and the taste of the food. So if you go to a restaurant and the service is excellent and the food tastes wonderful, you would feel inclined to give a higher tip. But if you go and the service is terrible and the food is terrible, then you can be inclined to give a lower tip. So we'll do that. So our first input, I'll click on it so that it will be highlighted. Then I can come under name and I would enter service. That's the first parameter we are considering. Then I will come under input 2, click on it so that it will be highlighted. I will change the name to, let's use taste or food taste. Or actually, okay, let me just put food. Okay. So service and food. Okay. Now the output, I click on it once so that it will be highlighted and I'll call it tip. So remember, we only change the variable names. The AND method will still stick with minimum, or method maximum. Aggregation, the way it aggregates the output at the end of the day will just stick with max, and the falsification will stick with centroid. Now, the next thing is we define our membership function. So this time around, let me invert. For the input, let me use triangular, and for the output, let me use trapezoidal, just for the fun of it. So I would edit. You don't always have to remove all membership functions. You can simply, since we have 3 already here, you can simply modify the 3, but I just like doing it. So I can add specifically the triangular membership functions and the number. So now we can have, okay, we are starting with service. So our service, let's just use a range of 0 to 10, basically. And for the lower service, we can say the service was 4.
Excuse me, please. If the input is 2,
yes,
or more than 1,
yes,
can you have different membership function for each of the input?
yes, you can. In fact, let's try it even now. Let's use triangular for service, and let's use trapezoidal for food. So the first membership function should be 4. The second one, let's say the service, okay, it was good. Let's just call it good. And the last membership function, let's say it was excellent. So back to what we did earlier. Mr. James, what range would you consider the service to be 4?
Pardon?
If the service, 4 service, what range will you give it? We are using a scale of 0 to 10. So what scale would you give 4 service?
3.
So 0 to 3 is 4.
0 to 3 is 4, and no tip at all.
Okay, so we'll do 0. The midpoint, okay, let's say 1.5, then 3. The triangle should adjust itself. Okay, Mr. Abdulkadir, good service, Uncle.
We start from 3 to
3 to
6.
3 to 6. Okay, so 3, 4.5, and 6. I think that should be the midpoint. Okay. So from 6 higher, I think should be great service. So let's see, 6, 8, 10. Remember, we can always have overlap. Oh, sorry. I clicked on the wrong membership function. So I was still using, it was still highlighted on good. And that is why it was messed up. So you have to make sure it's highlighted on the right one, which is excellent. So that will be 6, 8, 10. Sorry. 6, 8, 10. Okay. So now we have that. So let's go to the food now. The food also would have 3 membership functions. And let's use trapezoidal to show that, okay, we can use different membership functions. So for the food, if the food tastes bad, should be the low membership function. Then the middle, let's call it okay. the food was okay, or the food was fine. Then for the last membership function, let's call it delicious. Okay. So, Oiza, what range do you think our food should be bad? We are still using a scale of 1 to 10, so I need to correct the range from 0 to 10. So what range is food bad?
0 to 3.
0 to 3. Okay, so 0, 1.5, 3. But remember, now we are using trapezoidal, so we are using 4 parameters, not 3. So 0, 1, 2, 3. Okay. Akau, what food is okay? Is Akau there? What of Aibami?
Yes, sir.
Okay, what range do you think food is okay? That you consider okay?
7. 3 to 7, sir.
3 to 7. So that will be 3, 5, 7. Okay. Then anything. Oh, okay. Sorry. I keep using the triangular number. So it will be 3, 4, 6, 7.
No, sir.
Okay. Umar, delicious should be 7 to 10, right? Or do you think it should intersect?
Yes, delicious can start from 6 to 6, 7, 8, 9, 10.
Okay. So let's do 6, 7.
7, 9, 10.
Okay. 6, 7. Yeah. So let's use 9 and 10. Okay, good. So as you can see in this case, we have an overlap, which is completely fine. You know, there are many, if you go through literature, a lot of membership functions, you see they have overlap. So now let's go to the tip. We have 3 membership functions also. Let's stick with triangular. So for the tip, you can tip low. You can tip medium. And you can also tip high. Yes. So Mr. James, I think we started
Hello,
with
sir.
you earlier. You said if the food is bad, no tip at all.
Yes.
So low tip now should be what? Let's still use our 0 to 10, scale of 0 to 10. You can use any scale you want. You can use 0 to 100 in terms of percentages. You can use 0 to 10 or 0 to 5.
And no tip will be 0 to 30 now.
Okay, 0 to 30. So let's 0, 1.5, and 3. Medium. Abdulkader, what of medium? Abdulkader, are you there?
Yes,
Okay.
I'm there. Take 3 to 7.
3 to 7. Okay. 3, 5, 7. Oiza, what do you think a tip?
Yeah.
Is Oiza there? Okay, Umar, do you want to give us the high tip?
Yes, from 7 to 10.
7 to 10. Okay, so 7. 8. So that's good. Now let's go to the rules. We've defined the membership function, so we now edit the rules. Okay. So now if you look at the rules down here, you will see that service is poor and food is, you see, if service is and food is, then tip is. So this is where the and or play. This is where you decide whether you want to use and or. So what we'll do here is everybody would give me, yes, everybody would give me a rule that would work with. So I'll start with James. What should be our first rule? You remember, you can use and you can use or, anyone. Hello, James. Okay, James is off. Okay, so Abdulkader, can you start us off?
Yes, sir.
Okay.
If the service is poor.
Okay, service is poor.
And the
And
food is bad.
Food is bad.
No tip. That is low.
So the tip should be low. So we've added the row. Is James back?
Yes, I'm back.
Give us a rule.
Okay, if the service is good.
Okay.
And the food is poor.
Okay, and the food is poor. Okay.
And the food is bad.
Okay. The tip
no
should be
motivation.
What?
No motivation for tip also.
So it will be low.
To be low.
Okay. Aibami, can you give us a rule?
If the service is good,
okay,
and the food is good, or the food is excellent, and then the tip should be high.
Okay, so if the service is good and the food is delicious, the tip should be high. Okay. Oiza, can you give us a rule? Try using or now instead of we already have 3, and so you can.
Okay, if the service is excellent.
Okay.
Or the food.
So now
if the service is poor.
Okay.
Or the food is good.
Okay, so now to use or, I need to come to the connection and change it to or, and it will change up here.
Okay.
Okay, and the food is, or the food is.
Or the food is good.
Good, okay. Then the
That's
tip
delicious.
is. No. Okay, delicious, okay.
Yes, the tip can be medium.
Okay.
Yeah.
I can add one. Okay, Omar, do you want to give us one more?
If the service is medium.
Okay, service is good.
Or
the
food is medium also. So okay. Then there's tip. It will be high.
It should be high. Okay.
Right.
Omar is very generous. So okay, so we'll add the row. So let's stick with 5. There are many possibilities, now from what we've done now, there are many configurations you can use the and or. So sometimes when you have results that you're not too happy with, you can always come back and modify the rules a little bit and see whether that would improve your results. So we can always view the rules, or before we view the rules, let's view the surface so that you see what I was talking about. So you can now see that the surface is this 3D, because you have 2 rules now. It's a 3D representation. On the x-axis, you have the tip. Sorry, on the y-axis, you have the tip. On the x-axis, you have the food, and on the z-axis, you have the service. Between input and output. And you can always view the rules.
Textbook like this. Confusing.
So when you look at the rules now, you can see that like we did earlier, there's always one extra box at the end of the output for aggregation. So if we put in a value, now if you look at the input, you will see that it's also in the square brackets, but there are 2 values separated by a comma. The first value is for service, and the other value is for tip. So now let's put in 2 values. Let's put, let's say the service was 10, but the food was not so good. Let's say it's 2. Then we'll click enter. You will see that it's given a medium tip. It's given a tip of 5. If the service is 10 and the food is 2, it's given a tip of 5. Okay, what about if the service then it has also given a tip of 5. Now, ideally, you would think that if the service is 10 and the tip is 10, it should give a high service, right? Are you with me? Normally, if the service is high and the food is also high, you would expect it to give a tip that is high.
Hi.
Yes, sir.
But in this case, it's giving us a tip that is medium. So this was what I was talking about, that if you feel the results are not so good, then in this case, this is not really the result you want. You can always come back to the rule editor and change or add a rule that would, influence that decision. So we can add a excellent, and the food is delicious, then the tip should be high. And we can add that rule. And now we can view the rules again, and we can try again and see whether that would influence it. So we can say 10, 10, and it's still giving a tip of 5. So yes, so another thing that can cause this is some of the rules. You remember the rules are aggregations. So some of the rules might be interfering with this last rule that is 6. So if you remove, let me see.
Let's
There are 2 rules here that talk about food being delicious. Rule 3 and 4. So let me delete those rules and see whether it will give me. So I've deleted those rules that influence delicious food. Now I only have my last rule that talks about excellent service and delicious food. So let's try again and see. So I can do 10, 10, and it's still giving me a tip of 5.
I think you have to remove that medium and medium that will give high. That is
high. That will give
yes.
high. Okay.
Yes.
So let me try that.
Medium that will give high.
So let me remove that. And let me view the rules again. So basically, you can see what I'm talking about. Sometimes you don't have the results you want, so you have to keep tweaking until you get the kind of results you're looking for. And it still hasn't changed. So that's one thing about fuzzy logic. Sometimes you have to tweak and tweak and tweak until you get the results desired. So let me just leave only that rule and see whether it would. Let me just leave one rule. If service is excellent and food is delicious, then tip is high. And let me use that. Let me use that and see whether it's from our rules or it's from the designer itself. And it still hasn't changed. So you see, in this case, I don't think the problem was from the rules. It could be, maybe the problem is from the membership function. Let me try 9 and 9, maybe because it's boundary values. Aha, so you can see 9 and 9 gave us a higher value. So maybe the problem wasn't even from the rules itself. Maybe it was just
I think it was from that when you are labeling the function, you use 7, 8, 9. I think something like that. I think 10 was excluded.
Okay.
You can check that.
Okay.
The range.
So the range. No, the range is 10 for output. Okay, let me check input. The last range is also 10. And let me check food. The last range is also 10. But 10 is a boundary. It's at the end. So I think that's why we were getting results like that. I think it's because all the 10 were all represented. But I think if I modified this, let's say to 11, the last one, and correct this to 11 as well. Yep. So by that time, if I view the rules now, I have only this rule. And if I try the 10 and 10, if I'm not mistaken, I think it should work. You can see that it also gave us a high tip. So I think it's because it was at the boundary. That's the reason. So but basically, this experience has shown what
can we try the lower boundary? Can we try the lower boundary and see?
Okay, with 0, 0.
Yes.
Okay, let's try 0, 0. I don't think we should have an issue with 0, 0. Oh, you can see the lower boundary gives us middle, like before. Yeah. So let's try 1, 1. Okay. Oh, but you know, I removed all the rules. We don't have any rule talking about the lower.
Okay, okay.
Yes, so you can tweak around and see how it behaves. So, but basically that's so you can always export. You can export to workspace. You can export to file, but let's export to file, and let's call.
We are going back to village.
Sorry. Oh, okay.
Sorry, sir.
No problem. So let's call this table for 2. And if we go back to our MATLAB, we should have table for 2 here.
Yeah.
Yeah. So you can always say my FIS is equal to read face
table for 2.
Table for 2 dot FIS. And it then you can see tip is equal to eval face my face comma. And this is why now I said you should use the square brackets, because you have 2 inputs. You have to put in 2 values here. You cannot put in 1.
Yeah.
So that would be 10 space 10. You can use a space or you can use a comma. Either way, it will still work. And you have your tip for 8.5.
Which is
and
high.
You can also, yes, you can also go back to Simulink, what we did earlier, and double click. And all you have to do is change the FIS name here to table for 2. FIS and click OK. But now, if you run this, you would have an error because you only have one
input
going into the fuzzy logic controller. And because you only have one input, the fuzzy logic box only has one input coming in. So it means you have to find a way to feed in 2 inputs. To do that, what you do is you can duplicate this. You can go back to the library browser and add another constant, which is here. So the first constant should be 10. And the second constant can be 10 too. And as well. Now, how do you feed in these 2 into this one? You use what is called a multiplexer. So the multiplexer would combine 2 signals and feed it into this thing. So you can come to commonly used blocks. You see MUX. That is the multiplexer. Then you add the block to the model. And you can bring it here. When you double click the multiplexer, you can change the number of inputs. So now we have 2 inputs we can use it. But if you have up to 4, you can change it to 4 and you see 4 arrowheads. But now we're only dealing with 2, so you can stick with 2. So you drag in the first one into one, the second one into the other, and you connect the output here. And when you run this, we should have our same value of 8.5. Right. Yep.